Hi guys, and welcome back to another talk through of our book Quantum Atom Optics, Theory and Applications to Quantum Technology. So where we were up to last time, we completed chapter 1. So this was just introducing the mathematical notation that we need to cover many quantum many-body systems. And so now we're going to go on to chapter 2, which is talking about Bose-Einstein condensation. So there's a couple of ways of looking at this, and what we're going to start with today is a kind of somewhat more informal way of understanding why you get Bose-Einstein condensation to start with. Well, firstly, I should say you should probably be familiar with this kind of phenomenon of Bose-Einstein condensation. This is when, if you start with a large, say, gas of atoms, then all the gas of atoms, they go into the ground state below some critical temperature. And so this is some kind of phase transition which occurs, and this was originally predicted by Bose first, and then Einstein later saw Bose's result and kind of confirmed that this should happen, and so they're kind of both credited for this particular phenomenon. So I'm not quite sure exactly of the exact sort of exact argument that Bose and Einstein presented, but at least this version is somewhat my interpretation and my understanding of their original argument. So, if you find that, this is not exactly what they said, then, please, don't get too angry with me. I've embellished it for the purposes of what I think is a better way to kind of understand this kind of argument in general. Okay, so let's have a look at this. So we're going to chapter 2. Right. Yeah, here we go. So in chapter 2, a good place to start with is to sort of understand a kind of prototypical system. So let's consider thinking about n non-interacting two-level particles. And realistically, when you think about Bose-Einstein condensation, what you should probably really think about is some kind of say container. It's containing a large number of atoms in it, and these are all bosons, and then you cool the system down, and spontaneously the system goes into the ground state. And the ground state would mean the ground state of the container that you are thinking about. So, if you've got some box here, what I mean by the ground state is, of course, so in a sort of idealized system, so here's our box, then the ground state would be some wave function, which would be just like you learn in the infinite square well. The ground state should be some Gaussian looking shape, or maybe sine curve, or something like this, right? So basically what you'd say is that all these atoms are in this same ground state below a particular temperature. That's basically the physics that we're looking for. But what we're going to do here is to not look at it so realistically. We're looking at a more sort of prototypical system. So what we're going to just consider is something a little bit simpler. So instead of looking at all these motional degrees of freedom, we're going to just basically think of a bunch of, say, two-level atoms. So these are all, say, atoms. We're not really going to particularly worry so much about the actual motional degrees of freedom, as would be a little bit more realistic, right? So we're going to consider a bunch of atoms, and we're not really, we're just going to consider each of them to be some two-level state, and there's an excited state for each atom, and then there's a ground state for each one, and we're just basically going to look at the thermodynamics of this kind of toy model, if you like, right? So we can view these particles in two different ways. So we sort of have a choice of how we enumerate the states of the system according to whether these particles happen to be distinguishable or indistinguishable. And what we're going to do is kind of contrast these two different cases and show that it gives really quite different results if you consider them to be indistinguishable or if you consider them to be distinguishable, right? So firstly, if we consider the case of indistinguishable atoms, so this is a little bit more like what we started off doing in chapter 1. So we there wrote down all the kind of Fock states of a system. And so because all these particles are indistinguishable, say you have well, here we've got 9 atoms, and say you've got 3 in the excited state, and then the other 6 are in the ground state, like this. So 6 atoms in the ground state. Now, because these guys are all indistinguishable atoms, the only way that you can really, and so are these, by the way, so these between these 3 and between these 6, they're all indistinguishable. So really the only way that we can enumerate the states of the system are using these bosonic operators that we learnt off in chapter 1. And so for this particular example, we would write this particular state as a Fock state, where if we call these atoms here, these are the atoms which we're going to be labeling by A1, and these atoms by A0 and A1, then this would be, and if we call K the number of atoms that are in the excited state, so there's 3 atoms in the excited state, so this will be Fock state number 3, and that means actually there's 6 A0s and 3 A1s, and then we need these proper normalization factors like this. Okay, so that's how we would write it for indistinguishable particles. But what if we had the same situation for distinguishable particles? So I forgot to mention that. So if we try and write down all the different states of this system, there are a total of only n+1 different states. So this K label just only goes between 0 and n+1. Oh, sorry, n, right? So there are a total of n+1 states because there's the 0 here involved too. So there's a total of n+1 states, and those are the full set of states that we have for the indistinguishable case. So what about distinguishable particles? Well, there we sort of have to count the atoms a bit differently, because now we can't just sort of group all these guys together and say, well, you guys are all indistinguishable, so we can't tell the difference between you, so the only thing that we can really say is that there's 6 of you in this lower energy state. In the distinguishable case, of course, so let me just do a 2-atom example. Of course, if this guy is down and this guy's up, this is a different state to something like this. So because we have labels on these particular atoms, so this is atom number 1, this is atom number 2, basically these 2 states are different states, whereas in the indistinguishable case, those we would say are exactly the same state. So in this case, we have a more sort of conventional situation, if you like. So this is a little bit more like what we're used to from classical physics. And in this case, we can actually simply enumerate what the state is of each particular atom. So there's n atoms. So in this case, we had 9 atoms here. And because each one is distinguishable, each of those atoms could be in one of 2 states. So that in that case, we have atoms either in state 0, state 1, or so forth. So in this case, the total number of states here that we can possibly have, so there are a total of 2 to the power of n states in the distinguishable case. So you can see that actually the number of states is totally different on depending upon if you consider them to be indistinguishable or distinguishable particles. So this is actually where the origin of this phenomenon of Bose-Einstein condensation will come from eventually. So anyway, so we'll get to that in a minute. So let's next write down what the energy spectrum of each of these are. And so I think I'm just going to jump straight to the figure that I've made here. So if we say that each atom, say either for the distinguishable or indistinguishable case, suppose there's some energy difference between these 2 levels of say delta E. This is what I called it here. Yes. Yeah. So each of those atoms are separated by an energy of delta E. So, and then if we say that this energy of the lower atom is 0, then in either case, for the atoms that are all in the 0 state, so for example, if we have this state, so here, let's do a 4-atom example. So all the atoms are in the ground state like this. So obviously they're all in the ground state. So the total energy of this system is 4 times 0. So it's 0. So if I were to draw the scale here, this energy here would be 0. This would be the ground state. Now, if we have one atom that is excited, then of course the energy is going to be delta E, because all but one of these atoms are in the excited state, and because the separation is delta E, so this one will be delta E. So either one will be delta E. Now there's a difference here, because as we said, in the indistinguishable case, there's really you can only really write down one state that has one excitation. And so the way that you would write that in this case is that A1 is just 1, that to the power of 1. And then this A0, there would be, say, n minus 1 atoms like that. And then if we normalize it, then it would be like so. So in the indistinguishable case, there's only that state is exactly that one. But for the distinguishable case, there are, for n equals 5, that's the example that I've drawn here, there are 5 different states which could possibly be the single excited state. So because there's 5 atoms, it could be any one of those 5, and that is basically these 5 states here. And then so I think you get the idea that if you've got 2 excited states, then this is a sort of a combinatorial thing. So then these are all the different states that you would get with, say, 2 excitations within 5 atoms. So I think this is 10. So because eventually this is a combinatorial where for each level there are n choose k number of states that satisfy this, right? So the spectrum in terms of the energies is identical, right? So this top state, for example, would be n delta E for either one. And in each case, these extremal states, there's only one state like that. But then for the distinguishable case, there's just a lot more states here that are in the middle. And if you know what a binomial distribution looks like, if we plot the binomial distribution, then this always looks something like a Gaussian, right? So there's a huge number of states right in the middle here where k would be, roughly n over 2, and there's a huge number of these ones because this would involve, factorials and so forth. Okay, so ultimately this difference in the spectrum is going to make a big difference. So so let me sort of skip one part here, maybe come back to it later, and give you the basic argument. So so now let's consider this system. So you have either an indistinguishable or distinguishable system, and there are some temperature T, right? So in either way, or in either case, they follow kind of Boltzmann statistics, because Boltzmann statistics simply says that if you've got an energy energy spectrum such as this, then the states will follow the probability of following of a particular state being occupied is going to be En over kBt, right? So whatever the energy of that state is divided by kBt, right? And then that's then there would be some normalization factor, which we normally call the partition function, right? And so if we were to try and say, or try and calculate, let's say we've got a bunch of atoms and they're all at some temperature. This whole ensemble is at some temperature T. So obviously some of these ones, so long that it's not like zero temperature, so some of these ones might be excited and some of these ones might be in the ground state, right? So because these are actually completely independent atoms, because it's you can kind of break this system down into individual components. There's actually a simple way of calculating the probability of finding how many atoms are going to be, say, in the ground state. And it's simply that you look at the system just on an individual basis. And basically because we can treat this whole thing as an ensemble and then do the calculation kind of the hard way, where we look at this entire spectrum, calculate the Boltzmann distribution for that, and then work out the probability of how many of these are going to be in the ground state, how many are going to be excited state. So we could do it like that, but we actually can get exactly the same answer, much simpler way, by basically saying that, these are basically independent, right? So even though we're going to look at this whole thing as a whole, let's just look at like one atom and then see what it does. And because these are all independent, actually it still holds for the whole system, right? So for a single atom, we can easily calculate the probability of it being the ground state, because so it's this Boltzmann factor. The beta is of course 1 over kBt, and then you divide by the partition function, which for a single qubit, so that's that Z factor which I was talking about, which is for a single qubit, it's just simply the probability Boltzmann factor sum of each of those two states. So this partition function is super easy in the case of a single qubit, and so the probability of it being in the ground state, like this particular atom, is simply equal to that. And this delta E is just defined as this delta E here is E1 minus E0. So that's just a separation between these guys. So so the probability is equal to this thing, and the key thing to notice here is that because these are all independent, this is actually independent of M. So it doesn't really matter how big your ensemble is, because these are not really interacting with each other. It doesn't really matter what n is. But in the indistinguishable case, actually it does make a difference, because you can't really, in this situation where we are treating these atoms as indistinguishable, we can't just sort of focus in on one atom and then forget about the rest, because really the spectrum and the set of states that you have with an indistinguishable bosonic system are kind of all, it's kind of linked to each other, and the properties of one are not really kind of separable from the remaining of them. So in this case, we really have to look at the full system as a whole and then calculate the Boltzmann probability of the spectrum, and then deduce what the probability is of finding each atom in the ground state. Okay, so the way that you do that calculation is a little bit different in this case. So in this case, the probability, what you do here is you say, okay, well, the energy spectrum looks like that. So that's just what I have on the previous page. And then the energy on the nth level is simply n. Oh, sorry, I used k, so let's go back. Okay, so the energy of the kth level is k times delta E, because each one of these ones is delta E. And then let's say that okay, for some reason I didn't start at 0 here, but if I started at 0, these factors will be not there. In fact, maybe if you do that, it's a bit simpler. So let's just say that, well, okay, just so that it matches with this equation, the energy of the ground state is E0. And so the energy of this state would be k delta E above whatever that is. And so for n particles, that would be n E0. So in other words, it's like we've got n particles in the ground state, but then we've lifted k of them out of it, right? Okay, so that's the energy level of that particular state. And then to find the partition function, then we have to sum over the probabilities of every possible state, and so that's why there's a sum here from k0 to n. So the possibility of either the state being here or here or here or here or here, and then actually, so this thing we can approximate very well by that. You can just stick that into Mathematica to convince yourself of that, and so the probability is equal to this. So that's the statistical probability of the state being in this kth level. And then what we're going to do is we're going to calculate, so for the average of the whole system, because sometimes it's in this state, sometimes it's in a different state, and so forth. And let's calculate the number of atoms that are in the ground state. So this N0 operator I'm going to define as being A dagger 0 A0. So that's the number of atoms that are in the total number of atoms that are in the ground state. So for example, this would count, so if you've got a bunch of atoms here, say this is your state, and say you had 2 atoms here in the ground state and then 1 atom in the excited state. So the operator N0 would basically just count 2 atoms that are in the ground state. So for example, this would return 2 for this particular state, right? Okay, so this counts the number of atoms that are in the ground state, and if we take an average over all the different states in the spectrum, then this time we actually get an answer that looks like this. And so here, what's going to happen is that it's going to be n minus this, and then so the fraction of atoms in the ground state would be simply this divided by n, and then now we actually get something with an n dependence. And if we look at the case where n is actually large, then actually this thing, so let's consider a fixed temperature, fixed energy, so forth, then this will be just some constant factor, but then this is a diminishing factor, so 1 over n is going to go to something very small, regardless of what this is. And so actually this is going to approach 1. So this is very interesting, because just because we counted things differently, of being either distinguishable or indistinguishable, we get an entirely different result for the number of atoms that are going to be in this lower energy state. And maybe sort of a casual way to understand this is that, because the spectrum is quite different, this Boltzmann factor is always an exponential. So if we kind of put our head on our side and then look at the exponential distribution, whoops, I don't know what happened there. Do that again. So exponential distribution, goes up like this. So here it's kind of natural to expect that there's going to be a high probability of states that are in this lower state. But we also have the same exponential factor over here, but then we have this very strong weighting towards the middle here. So even though this state by itself is way more probable than any of these other ones, but then because there's so many of these ones, all these ones add up, and it actually makes it kind of balances out this exponential, right? So because you have, as I said, this binomial factor, which in terms of sort of the number of states is weighted like this. So even though this is big here, this is actually small, and then the binomial is actually quite big here, where this is actually a bit smaller, and it kind of sort of cancels each other out in a way. So this is why it makes a big difference of whether things are indistinguishable or distinguishable. Okay, and I think maybe we might leave it there, because I don't want to start going through all these exercises. And also I missed a small point here regarding the symmetry, but I think we can cover that in the next lecture. So if you have any questions on this topic, I hope this was a bit helpful for you to understand how Bose-Einstein condensation occurs. And have any questions, leave it in the comments below. And it will be great if you subscribe to the channel and support what we're doing here. Okay, thank you.